Okay, the last thing we're going to look at with forces isn't really any new physics, it's just a different situation, and I want to show you some problem-solving skills, I guess, for boxes on ramps, sometimes called inclined planes. So we'll start out with a fairly simple situation where we assume there is no friction. I just have a box on a frictionless ramp at a 30-degree angle, and I want to find the acceleration of this box. Okay, so if we start out looking at the forces acting on the box, I've got a gravitational force pulling straight down, and I have a normal force from the ramp pushing straight out from the ramp, not straight up. This is perpendicular to the ramp. And if I want to figure out the acceleration, I need to think about the forces in the x and y direction and whether they're balanced or not. Well, this is a little bit complicated because my acceleration is not just in the x or y direction, it's down the ramp, which is a composite of the x and y direction. So you could solve for each component of the acceleration in this picture and then put them together, but that would be a longer, harder way. The easier way to do this is to change our perspective. So if you imagine tilting your head to the right a little bit, such that the normal force is pointing straight up and now gravity is pointing off at an angle. It's not that it's actually changing anything, it's just changing the way we're looking at it. So our free body diagram will look something like this in that case. Another way to think about that is if I just rotate this guy that way and this guy that way, we get this picture here. We need to be careful about where we indicate our angle here. So this guy, in order to rotate straight up, had to rotate to the angle of the ramp. So this guy rotated 30 degrees, that guy rotated 30 degrees, which means it's our vertical angle here on gravity that is 30 degrees. Be careful with that. Don't put it down here or you will have your sines and cosines crossed. So in this picture here, we can now think about breaking up gravity into components, which is a little strange at first because gravity is always straight down. But it will make solving this type of problem a whole lot simpler. So I have an x and y component of gravity. Well, my acceleration in this picture is just to the right. So all I need to worry about as far as my acceleration is the x component of gravity. Let's look at our equations anyway though. So in the vertical direction, taking vertical from this picture, not from this picture, we have balanced forces. So we can say that the normal force, the forces up, are equal to the forces down, so the normal force is equal to the y component of gravity. We're not actually going to use that in this situation, but we will later on, so it's good to think about those things. In the x direction, we are accelerating down the ramp. Accelerated motion means, undo, there we go. Accelerated motion means we have unbalanced forces, right? So the equation we use there is F equals ma, where F is our net force. So that's going to be any forces in the direction of acceleration minus the forces in the other direction. Well, the only force we have at all in the horizontal direction is the x component of gravity, so we can set Fgx here equal to ma. To find Fgx, we would do mg sine theta, the x component of gravity, set that equal to ma. Masses actually cancel out, so my acceleration, if I switch sides here, is g sine theta. You might want to make a note of that. That is always going to be the equation for the acceleration of a box down a ramp in the absence of friction. So only if there's no friction. Then you get this nice simple equation here. G is 9.8 sine of theta. That's 30 degrees. Sine of theta is a half, so this is 4.9 meters per second squared. You might ask, why are we doing boxes and stuff instead of maybe a ball rolling down a ramp? The answer is a ball rolling down a ramp is a little bit more complex. You have to deal with rotational inertia and things like that. So we are not going to look at those. We'll stick with boxes. They're nice and easy. Alright, so there's kind of a first pass. This rotation thing here is key. You really want to do that with every ramp problem, or life will be much more difficult. Now let's throw friction into the mix. we would also need to know the mass of the box when there's friction. Here I didn't give you a mass, but we ended up not needing it. The acceleration of any box on a frictionless ramp is independent of the mass. In the real world there is friction usually, so that is going to complicate our situation a little bit. I've got the normal force up and over, and gravity down, and friction will be in the opposite direction of motion. So I'm going to put friction this way. And let's just say that we are given the mass of the box is 20 kilograms, and let's say we know the amount of friction in this case is 10 newtons of force. So in the x direction and in the y direction, we can make our equations again. Again, we want to rotate this picture, so I've got a normal force up, frictional force to the left, and a gravitational force down and to the right, which again I can break up into vertical and horizontal components. Make sure to label your angle there. The vertical angle is always going to match the angle of the ramp. So again, we've got the normal force equal to the y component of gravity. Here we've got unbalanced again, so net force equals ma. But in this case there's more than one force in the horizontal direction. Fg, not Fy. Or F. Okay, here we go. So I've got this guy to the right, that guy to the left. My acceleration is in this direction, so I'm going to do Fgx minus friction equals ma. Fgx is still mg sine theta, but there's no m in our friction here, so I can't cancel out the m's. But I have all these values now, so I can still plug in and solve for acceleration. I've got 20 for my mass, 9.8. Sine of theta is a half, sine of 30, so I'm just going to do 0.5 minus friction of 10 equals 20 times A. All of this stuff works out to be 98. Half of 20 is 10 times 9.8 is 98. Minus 10 equals 20A. 88 over 20 is equal to our acceleration, and that works out to be 4.4 meters per second squared. So last time we had 4.9 with the same box on the same ramp with no friction. If we add friction, we would expect it to accelerate a little bit less. So not too bad, right? Just adding a few more things to our equation. Let's look at one other situation where I'll throw everything at you, all of the wonderful physics you've learned so far. And as long as you just take it step by step, it's not too bad. Let's say that we've got our same 20 kilogram box on our same ramp. But now I don't tell you about the amount of friction there is. In fact, I want you to find the coefficient of friction. And I'm going to give you some kinematic information. Let's say that it takes 2.4 seconds for the box to travel, let's go with 1.5 meters down the ramp. Okay, so I mean it's traveling in this direction 1.5 meters. Okay, if that's how long it takes for it to travel that far down the ramp, we can use that information to solve for the coefficient of friction. Well, this little part here is just to help us find the acceleration. And if I consider this to be the x direction down my ramp, then it doesn't matter that it's not vertical or horizontal. I can, again, kind of take that rotated picture, right? So I can say delta x is v naught t plus 1/2 at squared. Let's also assume that this started at rest. We'll assume v naught is equal to 0. It doesn't have to be, but this way we don't have a quadratic and make things even longer. Alright, so I've got my delta x there is 1.5. This goes to 0. I have 1/2 times my acceleration. This is not gravitational acceleration, right? We're not in free fall here. We don't know what our acceleration is. That's what we're going to find here, so that we can use that with our force analysis in order to find this coefficient of friction. Alright, we've got the time, so 2.4 seconds squared. Just square the time, not the rest of this stuff. Okay, I rearrange, I'll kind of skip a little bit of the algebra. It works out that your acceleration is 0.52. I'm going to use this value again, so I'm going to write down several digits. If I were using my graphing calculator, I would just keep all the digits that the calculator could keep. Alright, so if this is my acceleration, I want to find that coefficient of friction. Well, I don't know exactly, just off the top of my head, how does acceleration work into coefficient of friction. So where you always want to start is with your free body diagram. So we still have same forces acting as before. We just don't know the value for friction this time. Okay, and if I rotate that guy, I end up with a picture like this. I always want to rotate it. There's my 30-degree angle. Okay, gravity here, normal force here, friction here. In the x direction, I've got, just like before, I've got the x component of gravity minus friction equals ma. In the y direction, I have normal force equals the y component of gravity. This time we're actually going to need this. Okay, so let's see where we can go from here. Well, we've got mg sine theta for this guy. Friction, I don't know what it is. But I do know that friction can always be found by doing mu times the normal force. Well, I don't know the normal force either, but I can find it by doing FGY. So this is mu times FGY. And FGY is going to be mg cosine theta, because it is this side of my triangle here, right? So if I plug that in, minus mg cosine theta, I can set that equal to, oh, I forgot my mu. It's important since that's what we're solving for. Equals ma. We can actually cancel masses out again in this particular situation. So let me rewrite this, get a little cramped there. So I've got g sine theta, sine of 30, minus mu g cosine of 30 equals my acceleration. So from this point we can just plug in some numbers. I've got 9.8, sine of 30 is 0.5 minus mu times 9.8 cosine, I don't remember cosine of 30 off my head, equals the acceleration that we found here from our kinematic information, 0.52083. From this point it's just algebraic manipulation. I don't really have room on this page and don't want to copy it onto the next. So I'll just tell you, when you rearrange all of that, you end up with a coefficient of friction of 0.516. And the coefficient of friction is unitless. So there you go. That kind of puts it all together. Have a good one. See you next time.